Okay, in this video I'm going to be talking about the Maxwell-Boltzmann energy distribution diagram. This diagram is used to help us to explain the effect of various different factors on the rate of a chemical reaction. So in the Maxwell-Boltzmann distribution diagram we have two axes. On the y-axis we have an indication of the number of particles, which is sometimes also labelled as the probability or the frequency. And on the y-axis we have kinetic energy. Now, in a system, every particle has a certain amount of energy, and that amount of energy does have a lower limit. It's not possible to have any less than no kinetic energy whatsoever. That would involve the particle being stationary. So the diagram has to start at the origin, where we have no particles with no kinetic energy. After that, as we increase the kinetic energy, we will have more and more particles having more energy, and it will follow a normal distribution pattern. So we will see a shape looking like this. However, unlike at the lower limit, there is no upper limit to the amount of energy that a particle can have. So the diagram will taper off and approach the x-axis, but it will never actually reach the x-axis. Okay? And this indicates that particles can have nearly no energy, but as we have higher kinetic energies, more and more particles will have more and more energy, until we reach a point where most of the particles have a roughly similar amount of energy. And then as we exceed that energy, the number of particles with higher energies drops off, but there will always be a few particles which are very, very energetic, and there is no upper limit, so we can keep tapering this off and it will keep approaching the x-axis, but without actually ever reaching it. Now, the area underneath the curve indicates the total number of particles in the system, since this is measuring the probability of a particle having a certain amount of energy here. A few things we need to be able to label on this diagram. The first is that if we draw a line halfway through the curve, so to the left of this line we have 50% of our particles, to the right of the line we have the other 50% of the particles. This line represents the average kinetic energy of the particles, and this actually corresponds to the temperature of the system. So temperature is a measure of the average kinetic energy of the particles in a system. And the temperature doesn't actually depend on how many particles there are. If you have a small amount of substance or a large amount of substance, the temperature is the average. And so, for example, if you have a beaker of water or a swimming pool full of water, they can both be at 20 degrees Celsius. They will both have the same temperature, although obviously there is significantly more energy in the swimming pool since there are far more particles in there. So this is the average amount of energy in the system, and half the particles have more, half the particles have less. We can also, on this diagram, draw another line, and this can be at any particular point. A vertical line here indicates a certain energy threshold above which the particles will have enough energy to react. And we can label this as the activation energy. So particles which exceed this energy, so they have more energy than this threshold, they will be able to take part in a chemical reaction, and any particles which do not have that amount of energy, which is the majority of them, will not have enough energy to react. This point will depend on the specific chemical reaction. Some reactions can have much lower activation energy, some can have much higher activation energies, but that threshold is a fixed value. What's important to note is that particles can gain and lose kinetic energy through collisions all the time. So a particle which is floating around down here with a small amount of kinetic energy can be bumped into by a more energetic particle, can gain kinetic energy and can cross this threshold and therefore become able to react. So it's not that a particle will be stuck down on this left-hand side of the diagram. They can move around and can gain and lose energy, and therefore non-reactive particles, or particles with not enough energy to react, can become able to react if they gain enough kinetic energy through collisions. So the area of the graph represents the total number of particles. If we were to increase the concentration in the system, essentially what would happen is we'd have more particles, and therefore the area of the graph would increase. So increasing the concentration, if you wanted to represent that on a Maxwell-Boltzmann distribution diagram, you would simply have to make the curve bigger. And if you have a bigger curve, then the total number of particles which would exceed the activation energy would increase. So I'm going to draw a faint line here. And you can see that this follows exactly the same pattern. The temperature, the average kinetic energy, is in exactly the same place, but we now have more particles able to react. We don't normally use the Maxwell-Boltzmann diagram to represent an increase in concentration, but we can see the effect of concentration by visualizing this. And pressure would work very similarly if we're talking about gases. If we have a higher pressure, we are confining our gases into a smaller volume. We're effectively increasing the concentration of particles in the same volume, and therefore will have a similar effect. So more particles will exceed the activation energy, and therefore the rate of the reaction will increase with an increase in concentration or an increase in pressure. It's more commonly used to show the effects of temperature and catalysts on the rate of reaction. Now, if we increase the temperature of a reaction, we are increasing the average kinetic energy of the particles. Now, we still have the same number of particles, so the area of the curve must remain the same. However, if we increase the average kinetic energy, temperature increases, the bump has to move to the right, but it has to keep the same area. So it still has to be anchored at 0. But our line, our curve, will now follow a different shape. Where the curve is shifted entirely to the right. Now, the area of the curve is the same. We have the same total number of particles. The temperature is higher. The bump has moved to the right, so the average kinetic energy is higher. And we can see that the area between the two curves here on the left should be pretty much the same as the area between the two curves here on the right. So we've basically shifted these particles across over here. And in order to do that, the peak of the curve has to shift both right and down. And we usually show this by making sure that the bump, the average kinetic energy, is to the right of and lower than the original bump, and usually just outside the curve of the original temperature. So we have the same area in the curve. However, we now have significantly more particles with an energy which exceeds the activation energy. So significantly more particles as a proportion of the total number of particles are now energetic enough to react and can take part in the reaction, and therefore the rate of the reaction is going to be significantly faster. Whereas originally we had maybe 10% of the particles capable of reacting, we now have perhaps 30% of the particles capable of reacting, and therefore the reaction will happen much, much quicker. So you must be able to represent the effect of temperature on the rate of reaction using the Maxwell-Boltzmann energy distribution diagram. The other factor which can affect the rate of the reaction, which you must be able to represent on a Maxwell-Boltzmann diagram, is the effect of a catalyst. Now, catalysts work by providing an alternative pathway for a reaction to follow with a lower activation energy. So they are moving this threshold, and they're moving it to the left. So if we draw another line here, we have a catalyst present in the system. We've shifted our activation energy to the left by providing an alternative pathway for the reaction, and this has therefore allowed another proportion of particles to react which were not able to react before without the catalyst. So now, with our original temperature, these particles in here can now react, which is again an increase on what was available before, and with our higher temperature, these particles in this section are now able to react, again a significant increase on what we had before, and therefore again more particles are able to exceed the activation energy and take part in the reaction. And we can represent that in the Maxwell-Boltzmann diagram by shifting our activation energy line to the left. Now that's the only way in which this line can move is if we are having a catalyst present to help the reaction. Otherwise, the activation energy is a threshold, it's a specific amount of kinetic energy, and particles must exceed it. It can't move towards the particles unless we are providing a catalyst with an alternative pathway with a lower activation energy. So these are the ways in which a Maxwell-Boltzmann energy distribution diagram can help us to visualize the factors which can affect the rate of a chemical reaction.